Imagine a storm. Dark clouds gather on the horizon, their bellies heavy with rain. The wind begins to howl, whipping through trees and rattling window panes. Then comes the flash of lightning, a jagged spear of pure energy that momentarily turns night into day, followed by the deep, resonant rumble of thunder that you can feel in your bones. For most of human history, this was the entire story of a thunderstorm, a dramatic, sometimes frightening, but ultimately familiar display of nature's power. But what if there is more to it? What if these storms are hiding a secret far more profound and cosmic than we ever imagined? Hidden within the chaotic turmoil of a common thunderstorm is a phenomenon so powerful it rivals some of the most advanced technology ever built by humankind. The same kind of process that happens inside colossal, multi-billion-pound machines, like the Large Hadron Collider at CERN, where scientists smash atoms together to unlock the secrets of the universe, is also happening high up in the clouds during a storm. In the early 1990s, NASA launched the Compton Gamma Ray Observatory, a sophisticated satellite designed for a specific mission to map the gamma ray sky. Its purpose was to detect the most energetic forms of light emanating from cosmic phenomena like black holes, pulsars, and distant, exploding galaxies. Scientists were expecting to catalog the violent events of the universe, but they soon found something completely unexpected. The observatory started registering incredibly powerful, short-lived bursts of gamma rays that weren't coming from deep space at all. They were coming from Earth. The data clearly showed they originated from the top of our atmosphere, in regions where large thunderstorms were known to be raging. This presented a major puzzle for atmospheric scientists. Their models of thunderstorms and lightning were well established, but they contained nothing that could explain the generation of such fantastically energetic radiation. To truly grasp the magnitude of what scientists were looking for, we first need to understand what antimatter actually is. Put simply, antimatter is the mirror image of ordinary matter. This idea didn't come from a wild guess or a sudden observation. It was born from the elegant world of theoretical physics, specifically from the equations of a brilliant physicist named Paul Dirac back in 1928. He had predicted the existence of an anti-electron, which we now call the positron. This concept extends to everything. When a particle of matter and its corresponding antiparticle meet, they don't just bump into each other, they annihilate. The two particles instantly vanish, their entire mass converted into a brilliant flash of pure energy. Scientists at places like CERN have managed to create and trap small amounts of antimatter, but it requires extraordinary technology. When an electron and a positron annihilate, they reliably produce gamma rays with a very specific energy signature, 511,000 electron volts. This isn't just a random number, it's a fingerprint, a telltale sign that this exact process has occurred. To explain the immense power of terrestrial gamma ray flashes, scientists needed a new theory. The leading hypothesis that emerged is a concept with a suitably dramatic name, the relativistic runaway electron avalanche. Imagine a single free electron inside the cloud may be knocked loose by a passing cosmic ray from space. The runaway avalanche model proposes that in the very strong fields at the top of a thundercloud, this electron can gain more energy from the field in between collisions than it loses during them. This creates an exponential cascade, an avalanche of billions upon billions of electrons, all accelerating in the same direction, a colossal, fast-moving river of particles. The theory predicted that as these gamma rays race through the dense air of the upper atmosphere, some of them would carry enough energy to trigger pair production. A single, sufficiently powerful gamma ray, upon passing close to the nucleus of an atom, could simply vanish. In its place, a pair of particles would spring into existence, a normal electron and its antimatter twin, the positron. Suddenly, the theory wasn't just about accelerating existing particles. It was about forging entirely new ones, including the elusive and mysterious substance of antimatter. It meant that thunderstorms were not just particle accelerators, but also particle factories. The process would be a chain of cosmic proportions. The storm's electric field creates a runaway electron avalanche. This avalanche produces high-energy gamma rays, and then these gamma rays in turn create beams of both matter and antimatter. The breakthrough in the search for storm-borne antimatter came from an observatory that, like its predecessor, was primarily designed to study the cosmos. Launched in 2008, the Fermi Gamma Ray Space Telescope is one of the most advanced gamma-ray observatories ever built. While its primary mission was to unravel the mysteries of supermassive black holes, pulsars, and dark matter, its powerful capabilities made it the perfect tool to eavesdrop on Earth's high-energy atmospheric phenomena as it orbited the planet every 95 minutes. The Fermi team began to meticulously scan the data, cross-referencing every gamma-ray event that originated from the atmosphere with weather satellite data to confirm the presence of a thunderstorm below. The moment of discovery finally arrived in 2009. The Fermi team was analyzing data from a TGF that had occurred over a storm in Egypt. As they examined the data immediately following the initial gamma-ray flash, they found exactly what they had been looking for. The instruments had detected a burst of gamma rays with a very specific energy peak, clustered right around the 511,000 electron volt mark. It was the unmistakable textbook signature of electrons and positrons annihilating each other. Fermi had not only detected the annihilation signal directly above the storm, but had also tracked this beam of antimatter as it traveled a significant distance before it finally met its end, annihilating with electrons far from its birthplace. The discovery that thunderstorms, a seemingly ordinary weather event, can forge antimatter fundamentally changes our perception of our own planet and its place in the universe. For centuries, we have viewed Earth as a relatively calm oasis, a sanctuary of life governed by gentle geological and meteorological processes, set against the violent backdrop of a cosmos filled with exploding stars and ravenous black holes. This discovery shatters that comfortable illusion. It reveals that our planet possesses a hidden, violent side, capable of replicating the kind of high-energy phenomena we once thought were reserved for the most exotic cosmic objects. This has opened up a new frontier for a very specialized type of storm chaser, one who's not just looking for tornadoes or lightning, but for the invisible signatures of high-energy particle physics. When we place Earth's natural accelerator and a human-made one side by side, we see two profoundly different approaches to achieving a similar end. A thunderstorm is a shotgun, spraying vast numbers of particles across a huge area. The Large Hadron Collider is a scalpel, meticulously preparing and directing particles for controlled collisions. The storm is no longer just a storm. It is a glimpse into the very heart of creation, a cosmic spectacle happening right here at home. We began this journey by looking at a familiar sight, the dark, churning clouds of an approaching thunderstorm. For millennia, we saw it as a mere weather event, a dramatic but understandable display of nature's power. Yet as we have discovered, this view was profoundly incomplete. Our exploration has taken us from the elegant theories of Paul Dirac to the cutting-edge technology of the Fermi Gamma Ray Space Telescope, and the conclusion is as breathtaking as it is undeniable. The storms that roll across our planet's skies are not just making rain, they are forging antimatter, acting as colossal particle accelerators that rival the most extreme phenomena in the known universe. This discovery collapses the distance between the terrestrial and the celestial, proving that the most profound mysteries of physics are not just out there, but are also woven into the very fabric of our planet's atmosphere, waiting to be discovered. As we look up at the next storm cloud that gathers on the horizon, we can now do so with a newfound sense of awe. We are not just witnessing a weather pattern, we are witnessing a gateway to the fundamental workings of the universe. Each flash of lightning is a reminder that our world is an active, energetic laboratory, constantly performing experiments on a scale we can only dream of. The familiar rumble of thunder now carries a deeper echo, a whisper of relativistic electrons, gamma-ray flashes, and the fleeting beautiful existence of antimatter.